History of Vector Analysis, Episode 14, Discrete versus Continuous. You are here. Hey, welcome back. It's old Doc Goler. In the previous episode, I discussed a bit of the history of the classical field on the grounds that the electric and magnetic fields represented the on-ramp of the quaternion/vectorial approach to modern undergraduate physics. I discussed the difference between the continuous extended field concept of Faraday and the more discrete point-to-point model of Newton's action at a distance. In this episode, I want to elaborate a bit more on this quasi-philosophical view that there is a difference between discrete and continuous mathematics and also physics, which, though subtle, is something that the troubled physics major should be aware of. A minimal amount of philosophy. I ask you to bear with me. Whether nature is essentially discrete or continuous is apparently not a trivial debate. It goes back at least as far as the ancient Greeks, who argued extensively about it. Democritus, for example, argued for a reality that was inherently discrete. If you cut a piece of cheese, say, in half again and again and again, eventually you get to the point where you get a piece of cheese that cannot be cut any further. He would have referred to this as an atom of cheese, where the word atom translates as not cuttable. Others felt differently. At the time, humanity did not have the data required to resolve this debate. Some would argue that we still don't, but I'm not going to go there. Nature and external reality aside, two distinct types of math were used in Greece and elsewhere at this time. One of these, arithmetic and later algebra, involved discrete mathematical structures, specifically numbers. Numbers back then were not considered continuous. The other type of math was geometry, which involved lines, curves, surfaces, and volumes. Democritus aside, these mathematical objects were viewed as continuous. René Descartes is credited as the guy who first succeeded in uniting these two types of mathematics into one in the 1600s in his analytic geometry. He argued that a locus of discrete points that were all a uniform distance from a central point could in fact be interpreted as equivalent to a single circle. This was not trivial because it required there to be an infinite number of points in that locus for this to work, and the mathematicians of the day hated infinity, often for good reason. It was Descartes' work that inspired a young Newton and a young Leibniz to develop the calculus of infinitesimals, today known simply as calculus. See, the concept of limit, a discrete point or number, combined with a function's requirement to be continuous and differentiable, reflects the marriage of the discrete and continuous mathematics. If I ever finish the series that I started once on analytic geometry, I'll go into this in more detail, but this too is mostly a story for another time. Still, the mathematics we use to model physical phenomena can often be associated with one side of the family or the other. If you think of physics as the construction of mathematical models to describe at least the inanimate behavior of nature, the history of science shows that some branches evolved out of discrete math and others out of continuous math, and that these fondnesses for one parent or the other influence the way that we humans come to interpret that physics. Elementary kinematics, for example, treats collisions as discrete events, even if they don't call it that. Yes, all sorts of weird stuff goes on at the micro and nanosecond timescales, but most of the time the way we mathematically model a collision is to assume the conservation of momentum, and if the collision is elastic, the conservation of kinetic energy, and then treat the collision as a discrete event. Other examples of discrete physics include a lot of classical mechanics, which models a solid object as the sum, an infinite sum, but still conceptually a sum of a bunch of discrete little pieces. The same for statistical mechanics. On the other hand, if we consider how an electron moves in the presence of an electric field, we tend to mathematically model the interaction as continuous. Other examples of our physics models that tacitly assume continuity versus discreteness are thermodynamics, fluid dynamics, and elasticity. No little clumps of stuff here. Pressure, temperature, and density are modeled as continuous parameters. But hey, it's all just math, right? I mean, if we physicists wanted to, we could explore the actual discrete collision assuming, say, a continuous Coulomb repulsion. Likewise, we could quantize the electric field and consider the trajectory of an electron to be controlled via its interaction with discrete photons. So this isn't a physics problem, right? It's just two mathematical ways to look at the same phenomena, right? Well, I would argue that while nature may be independent of how we model it, we humans do have to struggle with the constraints of our mental capabilities. One of these constraints is that we tend to divide the world up into dichotomies, living versus non-living, good versus bad, higher versus lower, etc. I would argue that this discrete versus continuous dichotomy reflects the way in which humans tend to model external reality. As a physics illustration, I point out the struggles that we have with that pesky wave function in quantum mechanics. Is an electron a discrete particle? Or is it a continuous wave? Is it localized or distributed? Okay. Part of what bothers us, I think, is that it feels like it ought to be one or the other, not both. That's not a physics problem. Okay. That's a human mind problem, but one that we all have. So I'm not going to go any further with this. I just want to point out that because even physicists are human, well, most of them, we do have a tendency to classify our models and even our physics models in this way. This brings us back to a very young William Thompson, whom we met earlier in this series, long before he became Lord Kelvin. In 1841, 10 years after Faraday introduced his law of induction, William Thompson was a freshman at Cambridge. It was at this time, as a teenager, that he wrote a paper showing how certain mathematical aspects of Faraday's E&M behaved in a remarkably similar way to the mathematical models of heat flow. Specifically, he showed that the mathematics expressing the lines of equal potential in an electrically conducting medium were mathematically identical to isotherms, lines of equal temperature in a heat-conducting body. This was a bigger deal than it might appear because electrostatics evolved out of the discrete-oriented action at a distance model, whereas heat flow evolved out of the continuity-oriented thermodynamics. So what, you may well ask? Two sides of the same coin, right? Not quite. Thompson noted that if electrostatics followed the same continuous mathematical rules as the more established thermodynamics, then perhaps there might be more physical connections as well. For example, heat required a medium to propagate through, and this propagation does not happen instantaneously. It proceeds over time. If Faraday's fields are in fact real and not merely a mathematical abstraction, perhaps their existence suggests that there is some sort of an electromagnetic medium as well, one that exists even in vacuum. Okay. What other physical similarities between these electric and magnetic fields and continuous phenomena such as heat might they possess? Thompson did not formally propose electromagnetic waves, but sometime later, building on Faraday's and Thompson's work on the existence of fields, James Clerk Maxwell would. I want to state that this interpretation of the significance of the discrete versus continuous perspective did not originate with me. I read about it in Crow's book on the history of vector analysis, which I have shown you before. But Crow did not originate this thought either. He quotes an older historian of science, E.T. Whitaker, who wrote A History of the Theories of Ether and Electricity in 1910. Crow presents an extended quote from this book, and I'm going to bite the bullet and read a large portion of it now because I think it's worth it. Okay, this is Whitaker's writing in 1910. In that power to which Gauss attached so much importance of devising dynamical models and analogies for obscure physical phenomena, perhaps no one ever exceeded William Thompson, and to him, jointly with Faraday, is due the credit of having initiated the theory of the electric medium. In one of his earliest papers, written at the age of 17 when he was a very young freshman at Cambridge, Thompson compared the distribution of electrostatic force in a region containing electrified conductors with the distribution of the flow of heat in an infinite solid. The equipotential surfaces in the one case correspond to the isothermal surfaces in the other, and an electric charge corresponds to a source of heat. It may perhaps seem as if the value of such an analogy as this consisted merely in the prospect which it offered of comparing and thereby extending the mathematical theories of heat and electricity. But to the physicist, its chief interest lay rather in the idea that the formulae which relate to the electric field and which had been deduced from the laws of action at a distance, thus discrete, were shown to be identical with the formulae relating to the theory of heat, which had been deduced from hypotheses of action between contiguous particles, a continuous medium. This paper, said Maxwell long afterwards, first introduced into mathematical science the idea of electrical action carried on by means of a continuous medium, which, though it had been announced by Faraday and used by him as a guiding idea in his researches, had never been appreciated by other men of science, and this was supposed by mathematicians to be inconsistent with the laws of electrical action as established by Coulomb and built on by Poisson. Okay, this is a reference to that violation of Newton's third law. The result of Thompson's memoir seemed to suggest a picture of the propagation of electric and magnetic force. Might it not take place in somewhat the same way as changes in the elastic displacement are transmitted through an elastic solid? Okay. These suggestions were not at the time pursued further by their author, but they helped to inspire another young Cambridge man to take up the matter a few years later. James Clerk Maxwell, by whom the problem was eventually solved, was born in ... Some of the value of this insight tends to get lost because the famous Michelson-Morley experiment of 1887 proved that the electrical ether suggested by Kelvin and then mathematically constructed by Maxwell turned out not to exist after all. Okay, but without the concept of an ether to kickstart him, it seems unlikely that Maxwell would have postulated the existence of electromagnetic waves, which do, in fact, seem to exist. Okay, that's the end of this digression on the history of the classical field. Recall that the reason I went off on this tangent is because it was Maxwell's attempt to better model Faraday's electric and magnetic fields that led him to introduce quaternions and the vectorial approach into mainstream physics. Okay, changing gears one last time, one final point. While these E&M fields were the motivation to introduce vector-based mathematics into physics, I must add that we do not need quaternions or vectors to mathematically model fields. In fact, Maxwell wrote his 4 major papers on E&M in the 1850s and 1860s, including his proposal for the existence of electromagnetic waves, without them. Rather, he used the standard computational technique of the day, Cartesian component notation. It looks like this: no quaternions, no vectors, no ijk's, just lots of letters representing different directions in space. Equations tend to be grouped in sets of 3s, one for each of the x, y, and z axes. The equation marked A at the bottom of this page would today be represented in the form of, vector D equals epsilon naught E plus P. William Thompson, the man whose paper helped lead to the acceptance of the reality of fields, would go on to fight against the use of quaternions to represent anything in physics for the rest of his life, as we will see. So here is perhaps some irony. Okay? The widespread use of modern vector analysis is not absolutely required in our physics, and its use today is neither mandatory nor inevitable. But having said that, this series is on the history of vector analysis, and the bottom line is that vectors came into use by physicists via classical field theory. Okay, the next episode I will introduce James Clerk Maxwell in some detail and describe one of the ways that he extended the concept of classical fields. See you then.